So today's session is centered on the topic role of AI and ML algorithm in electric vehicles, a field that is shaping the future of transportation and energy systems. To lead us through this fascinating topic, we are honored to have an exceptional expert with us, Dr. Amit V. Sant, Associate Professor at Pandit Deen Dayal Energy University, Gujarat. Dr. Amit V. Sant is a dynamic academician and researcher. He earned his PhD in electrical engineering from IIT Delhi in 2013. His research contributions span across advanced topics such as multi-level inverters, high gain DC to DC converters, renewable grid integration, and also the application of artificial intelligence in power electronic systems. Before his current role, he also gained valuable experience as a postdoctoral researcher at the Masdar Institute, Abu Dhabi. His work in EV charging infrastructure and power quality enhancement makes him an authority in today's topic. Without further delay, let us welcome our honorable resource person to take over and guide us through this exciting topic. Sir, we are eager to learn from your insights and expertise. Thank you and wishing everyone for an engaging and interesting session. Please.
Thank you, sir. Thank you very much for the introduction. Can I share my slides?
Sure, sir.
Yes, sir. Yes, sir.
Yes, sir.
Is the slide visible?
Visible, sir. Yes, sir. Visible. Yeah.
So thank you very much for this opportunity to share the area or the work that is being carried out by my group. So I will focus on the applications of AI in electric vehicle. So what is an electric vehicle? Before we go to that part, let's see that what is an electric vehicle. So, and what are the applications of AI in electric vehicle? So I have divided during my work electric vehicle into different parts. One is the propulsion system, the system that is responsible for pushing the vehicle to move on the road. Second one is EV charging system, battery management system, vehicle to grid. That means the battery located inside your vehicle is acting as a source and they're supplying active power to the grid. That is called V2G, vehicle to grid. So this will be particularly useful during the high demand period. Rather than having a peak power plant, different vehicles can share this. Also, when we have variable tariff system, you can charge your vehicle when the tariffs are low and you can supply to the grid when the tariffs are high. In this way, the vehicle owner can earn money as well. And whatever we do, the charging of the electric vehicle poses some challenges for the grid in terms of power quality. So we will try to see the impact of the EV charging on power quality. So first we'll try to have a look at all these systems and then we'll have a discussion about how AI, ANN, ML, fuzzy, they can be employed for these systems. So AI. So AI refers to, so this is AI can have many definitions. This is as per my understanding, AI refers to emulation of human thinking. How we think, how we take a decision, right? How we decide. That is emulated in the form of a mathematical expression. Let's say if it is cold, I will wear sweater. If it's not cold, I will not wear a sweater. So this is an if statement, right? So I can use it as an if statement. Similarly, a classical example is I go to a restaurant to have food. If the food is good and the service is good and the ambience is good, I will give a high tip. If the food is good and the service is not that great, but ambience is good, I'll give medium high tip, right? If the food is bad, I will give 0 tip. So like that. So this is a fuzzy. There is no 1 or 0, this or that. So we are in between somewhere, right? So that can also be one of the things. So what we are doing here is that AI for me refers to the emulation of human thinking. So how I think, I apply that in the form of mathematical expression. What does this mathematical expression involve? It involves mainly updation of weights for learning. So there are some weights. Every decision I can take, many chances are there. I may go out, I may not go out. I may sit, I may sleep. So many options are there. Each option has a weight, and the option with the highest weight will have most prominent impact, right? So when we are doing this learning of the weights, what we need a large data set. This data set should have input and output. So I'm going to map input to output in a linear manner or a non-linear manner. So this data set is of prime importance. Larger the data set, larger will be my accuracy here. So that is one of the aspects here. So artificial intelligence can include machine learning. Machine learning again involves classification problem and regression problem. Classification means we say it belongs to group 1, 2, or 3. Regression means it gives me a value, let's say 0.01, 0.02, and so on. Artificial neural networks. Neural networks are more like a black box. Your input data, output data. You train the network based on the input and output data, and then you give new inputs, and you will try to get a similar output. So neural networks involve different layers. It is input layer, hidden layer, and output layer. Input and output layer can be single. Hidden layer can be multiple. Each layer has a neuron, right? What is a neuron here? Neuron basically consists of a activation function. Means it will get inputs, different inputs, multiply with them by weights. So you'll get sum of weight inputs, and then based on that, it will affect to a mathematical function. The mathematical function can be a signum function. It can be a linear function. It can be a sigmoid function. It can be hyperbolic tangent function. Fuzzy logic. Fuzzy logic is where we say everything is not white or black. There is something gray, right? So we'll divide every decision we take is divided into like very high, medium, low, medium, depending on your experience or your thought process. So first we'll fuzzify, then we'll have a rule base. If the input is high, and suppose if the vegetable is fresh and it looks having less pesticide, it is better for health, right? If the pesticides are less but it does not look that fresh, it is not very good for your health, right? Things like that. So it is in fuzzy terms, good, bad, very good, very bad, things like that. Meta-heuristic technique are mainly used for optimization. They refer to random search algorithms. That means we are trying to see some natural process. Let's say how a bird eats a grain, or how a bee finds a flower, right? Based on that, we have imitated this process in terms of a mathematical equation. What we are doing by this, in the simplest way, if I say, we are trying to find out the best possible fit, right? So out of the many, we will try to have, out of the many possible outputs, right, we'll try to have the best possible output. One of the example, all of us have used PI controller, and we know that tuning a PI controller is a huge challenge. So how to tune a PI controller? So how meta-heuristic technique will work, right? We'll take an example of a simple buck converter with a voltage control. That means the output voltage is compared with a reference voltage, and based on that, something like this. Let's say an output, this is our reference voltage. It is compared with a actual voltage of output voltage of a buck converter. Let's say V0, and the resulting output is given to a PI controller. Right? The output of this PI controller is our duty cycle D, and this D will be equal to Kp into error. So this is my error, the difference. Kp is the proportional gain plus Ki into integral of E dt. So these values of Kp and Ki are very critical. Right? How to select these values? Someone will go with a mathematical explanation. They'll make a mathematical model and then implement. But often when we make a mathematical model for a buck converter, it's simple. But many non-linearities are there. Many assumptions are there. Because of them, when you employ this in hardware, this will not be exact as your simulation. The Kp and Ki will need to be changed. Right? So some people have thought that I will vary the Kp and Ky. What should be the value of Kp and Ki? So what they will do, they will use this error and duty cycle D, right? So they will check different duty cycles are there, different possible. Let's say 0.1 is there, 0.33 is there, 0.46 is there, right? So among them, and many more will be there, right? Many more values. Which value is selected has to be selected for the best possible outcome. So this treats this, let's say in terms of birds, it will treat them at each value of grain, right? Each position. So which grain the bird should pick, that will have the best fit. So like that, it will converge to one value. So final value, all your possible outputs of D will be same. And many more techniques are there in this. So before we go to that, let's have a look at what is electric vehicle. So as per EIS, electric vehicle, any vehicle propelled by electric motor drawing current from a rechargeable storage battery or any other portable electric storage device is termed as a electric vehicle. It is mainly used for public streets, road, highways. Then we have chargers. So chargers are power converters that perform necessary function of charging a battery. And what is charger? charging function, all functions necessary to condition a standard voltage and frequency AC supply current to a regulated voltage and current to assure proper charging of EV battery. So that means, see, your grid voltage is 230 volt RMS, peak value is 325, and it is AC. So I need to convert AC to DC. So if I connect the capacitor at the output of my diode bridge rectifier, the capacitor will charge to 325 volt. From that 325 volt, I have to charge the battery, but battery is just 48 volt battery. So I have to use a DC-DC converter to step down the voltage and charge the battery. While charging the battery, I have to control the battery current and battery voltage. So these are the how we will go ahead with. So we will try to have a look at the EV propulsion system, battery chargers, and SOC estimation. And after that, we'll try to check what are the applications of AI or ML possible in this. Right? Before we go to that, we'll try to see why we are studying this topic, because in 2020, China has implemented 5 million zero emission vehicles on the road. Right? India and Germany by 2030, they plan to have only zero emission passenger vehicles. The IC engine based passenger vehicles will not be produced at all. And by 2040, United Kingdom plans to ban petrol and diesel based vehicles. Right? Why are we doing this? If some of us have seen the movie Interstellar, they have shown that humankind has to find new planets because the earth is not able to sustain us. There are a lot of problems. The crops are not growing. The air is too polluted. People are falling ill. Something like that may happen to us. We have 2050 is our time till which we have to mend our ways and make go for more sustainable ways of living. Otherwise, we'll do like irreparable damage to our atmosphere and our earth. So to avoid that, one of the greatest reasons for carbon emission is automotive sector. So we want to shift from petrol and diesel based vehicle to the electric vehicle based vehicles, battery based vehicles. So let's have a look at the electric propulsion system. So this is the electric propulsion system. You will have a battery. The battery output will be DC. This will be fed to a bidirectional DC-DC converter. Right? It will change the voltage level. Let's say this battery is 48 volt and the motor requires peak value of, let's say, 76 volt. So here it will give 76 volt, right? Or even 80 volt or 90 volt, depending on that. Then your inverter. So what inverter does, it performs DC to AC. At the same time, at this point here, it controls phase, frequency, and magnitude. Three things. It controls the phase, frequency, and magnitude of the current so that the torque can be controlled. So major components of battery, it can be lead acid battery or lithium ion. These days we are going for lithium ion. Electric motors can be there. The thumb rule is for two-wheelers, we go for PM BLDC motor with trapezoidal back EMF. For four-wheelers, we go for PM BLDC motor with sinusoidal back EMF. The sinusoidal back EMF motor is also known as current magnet synchronous motors. Power converters needed are inverters and DC-DC converters. And again, as the vehicle moves, the battery will be discharged, so we also need a battery charger. The reason for bidirectional DC-DC converter is that when the motor is moving on the road, the power flows from lithium-ion battery to the motor. But at the same time, when we want to go for regenerative braking, that means rather than wasting the energy, generated energy, we want to feed the energy back to the grid, back to the back to the battery. That then this bidirectional DC-DC converter should allow the power to flow from motor to the battery. Why we are doing this? Because one of the biggest challenge for the electric vehicle is range anxiety. That means people want more, people are worried how much range it will go for. Okay? Other problem is how much distance I can travel over one full charge of the battery pack. So these are the issues. So what we are trying to do, rather than wasting the energy in the form of heat and friction, we are trying to feed the energy back to the battery so that somewhat I can charge the battery. However, I cannot charge the battery very fast, so other alternative might be the use of ultra capacitors, which can get charged faster. So electric propulsion system mainly deals with speed control. So this is the basic block diagram of speed control system. So power supply, our power supply is a battery. We have got a power electronic converter. This is DC to DC converter plus DC to AC converter, that is an inverter. We have electric motor that can be PMSM or PMBLDC. And we have a mechanical load. So here you have to take vehicle dynamics into account. What is the rolling load coefficient of friction? What is the aerodynamic drag? What is the mass of the vehicle? What is the acceleration? All those, based on that, mechanical load can be determined. Right? So as we know, power electronic converters, though they're highly efficient, they're dummy. They require some activation signal, which is the gate pulse, to tell them, okay, turn on now, turn off now. So gate pulse are generated by a controller, and controller is fed from feedback signals from sensing units. So if you want to control the speed of the motor, mainly two techniques are used, that is field-oriented control and direct torque control. We'll have a look at the two techniques. Field-oriented control is a decoupled control. That means in a normal, if I talk in terms of induction motor, you have got magnetizing component of current and the torque producing component of the current, right? So if you change the voltage, the flux changes, the magnetizing component of current changes, and the torque producing component of current changes. That means change in one affects the other. Decoupled control means if you change one, other does not get affected. It has drawn its analogy from separately excited DC motor, where you change the field voltage, the field flux changes. Where you change the armature part, the armature flux changes. Right? So torque is proportional to phi Ia in a separately excited, or phi F Ia, right? So if you change VF, phi F changes. If you change VA, Ia changes. This is a separately excited DC motor. So this we call as decoupled control. This is, we say, the best speed torque characteristics that we have, torque characteristics that we can have. We want our induction motor to have this torque characteristics. And for this, we have divided current into two parts. This is my torque producing component of current, I will call it IQ, and this is my current flux producing component of current, I will call it as ID. So I'm trying to control the two currents separately, right? That is where the vector control is. As compared to V by F control, it provides fast transient and excellent steady state response. So we tried to improve that and come up with another technique called direct torque control. So here we say that flux is proportional. In vector control, we say flux is proportional to ID, and torque we say is proportional to IQ. Right? However, we are not taking saturation. We are into account. We are not taking harmonics into account. We are making many assumptions. So direct torque control says no, you don't have to control the components of current to control torque and flux. I'm repeating. This fellow says that the flux is proportional to this current, torque is proportional to this current, and we are controlling the current. By controlling the current, we are controlling flux and torque. So torque and flux are indirectly controlled. Direct torque control says, no, this is not the right way. We will control torque and we will control flux directly. Right? That is what it says. So it's a type of V by F control, scalar control, and it said that it has better transient response than V by F control. It does not involve any modulation technique like sinusoidal pulse width modulation or space vector modulation, which are involved here. So this is a classical vector control block diagram. This is a PCM based simulation. So let's try to understand what is vector control, and based on that, we'll have a discussion of how AI will come into picture here. So this 6 switches, 1, 2, 3, 4, 5, 6. These 6 switches make an inverter. This is your battery, right? And DC-DC converter combination. I'm getting a regulated DC supply. And from here, I'm feeding it to induction motor. Or it can be any other motor, PMSM motor, though I cannot apply to PM BLDC motor. Vector control is suited for sinusoidal currents and voltages, right? Motor having sinusoidal currents. So this is fed to this motor. Motor is having a load. So I have this current sensors, 1, 2, 3, to sense IA, IB, IC, the stator currents. And I have this speed sensor. So current and speed are being sensed. Then what I will do, I will use this speed, right? And I'll compare this actual speed with the reference value of the speed. In electric vehicle, the reference value of the speed will come from the driver. The driver will give the command. Based on this, the commanded value of the speed will be decided. These two speeds will be compared, and the resulting error, right, which is having a unit of RPM, it will be fed to the PI controller. Now, the job of this PI controller is that I want to reduce my speed error to 0. So this PI controller does 3 things. One, it stabilizes the error. Then once the error is stabilized, it reduces the steady state error to 0, and it filters out the high frequency noise. These 3 things it is going to do, right? So the PI controller output is, we say, torque, right? Why? Because if I have a classical equation that TE, developed torque minus load torque, is equal to J d omega by dt, or if you say d omega r by dt, right? That means if T is equal to TL, J is constant, so d omega by dt will be 0. It will run at constant speed. The motor will run at constant speed when the developed torque equals the load torque. If the developed torque is more than load torque, then d omega by dt is positive. That means acceleration. If T is less than TL, then d omega by dt is negative. That means retardation. So I need to make the error speed error 0. If I want to make the speed error 0, let's say speed error is positive, I will increase the value of torque so that T is greater than TL. Because T is greater than TL, d omega by dt will be positive. And because d omega by dt is positive, the motor will accelerate. So this is reference torque I'm saying. But as I had said before, in vector control, we say torque is proportional to IQ and flux is proportional to current ID. Okay. What are ID and IQ? Yes, that is important aspect. ID and IQ are DC quantities. Right? But here you had current IA, you had current IB, and you had current IC. These are AC quantities. Right? So whenever we talk about AC quantities, we'll talk about three things: phase, frequency, and magnitude. But when we talk about DC quantities, only magnitude is there. There is no phase, there is no frequency. So here three quantities were there. And in those three quantities, again, phase, frequency, and magnitude, 9 quantities were to be controlled. Here, only 2 quantities. So from 3-phase, we brought to 2-phase DC. And these 2 DC signals are having only magnitude. So only 2 quantities are to be controlled. That is one reason. Second, our PI controllers are designed to handle only DC components. Okay. They are designed to handle only the DC components. So that is what we are trying to do. We are trying to control the DC components. So input should be DC. Okay. So this IQ command is the reference value because torque is proportional to IQ. Reference torque is equal to reference value of IQ. So reference value of IQ now I have. Right. So what I will do now, IA, IB, IC are taken here. These are low pass filters. Actually, the cutoff frequency is very high just to eliminate noise. Then I'll feed them to the ABC to DQ transform. This ABC to DQ transform is the heart of the system. Right? ABC to DQ transform is also called coordinate transform. Some people call it Clark-Mark transform. Some people call it 3-phase to 2-phase transformation. So this ABC to DQ is how? It is just a mathematical equation which converts the input ABC, IA, IB, IC into ID and IQ. One more input is required, that is theta. What is theta? Theta is theta is the integral of the speed, right? The position of the rotor. So we need to find out the value of theta. And so how will you find out the value of theta? So first we have got speed, right? So this is in RPM. We'll find out the electrical speed here using this block K. Then, but we have something like this, omega S we want. So omega S is equal to omega R plus slip speed omega SL. So how to find out omega SL? So that is a key feature now. So what we'll do, this IQ reference divided by this ID reference. What is your ID reference? ID reference is the magnetizing current at the rated voltage. ID reference is the magnetizing current at rated voltage. So this value will get. So this divided by this into time constant of the rotor circuit. Into time constant of the rotor circuit. So time constant of the rotor circuit involves rotor inductance and rotor resistance. Now we cannot directly measure the rotor resistance and rotor inductance. So first problem starts there. If these values are wrong, the system will go wrong. Okay. So I have got my reference value of Q and reference value of D. Both of them will be compared with the actual values and I'll get error ED and error EQ. Again, ED and EQ are fed to a PI, separate PI controllers here and here. And the output will be the voltages. So these are the VD and VQ voltages. They are DC quantities. But I cannot work with the DC quantities. I am not able to work with the DC quantities. So what I will do, again, I will convert DQ to ABC. Here we had done ABC to DQ. Now here we'll do DQ to ABC. Again, I'll got VA star, VB star, VC star. I'll feed this to a sinusoidal pulse width modulator and generate the gate pulses Q1, Q2, Q1, Q3, and Q5. That means for upper switches. Lower switches is just the knot of that. See here, the knot of that is applied to the lower switches. Anything you would like to discuss in vector control before we go to the part where we discuss about why ANN will be required and what are the problems? Please feel free to interrupt me anytime and have a discussion about whatever is going on. Right? I will not mind that. Okay, so what all problems are here? Let's try to see. Imagine you are driving an electric vehicle on the road. So the electric vehicle has this system installed to control the speed of the motor. And this sensor, speed sensor, this is my speed sensor. What if the speed sensor fails? What will you do? What will happen if a speed sensor fails in your vehicle? Am I audible?
Sir.
Yes. Someone has written right. It will be better if you speak out. The reason being, I am unable to, see there. I have to shift between the screens. Yes, if the speed sensor fails, that means output is 0. Then my control system will think, okay, speed is 0. Increase the torque, increase the current, so that the higher speed will be attained. But my speed is not actually 0. It has some speed, so it may result in some accident, right? So alternative is that if the speed sensor is not working properly, I should get a signal. The gate pulses should be stopped so that the motor cannot move it. But if the vehicle stops in between the road suddenly, it may also cause accident. So what it should do, it should give a signal to the driver that there is some signal or beep buzzer sound comes. So driver knows now there is speed, something fault is there. I need to stop my vehicle. So he can give some signal and stop the vehicle. How AI can come into this picture, right? So the role of AI will be this. One, it will check the speed sensor, right? What is the speed? How is the speed sensor working fine or not? Second, if speed sensor fails, then what it has to do? It has to go for sensorless control. What does sensorless control mean? Sensorless control means without any sensor, I'm trying to estimate the speed. If I give example of a DC motor, we have N is proportional to EB by phi, where EB is the back EMF and phi is the flux. I'm assuming my flux is constant. I'll say this is VA minus IA RA by phi. So I can write N is equal to some constant K into VA minus IA RA. So if I sense IA, if I sense VA, I can find out the value of N. That is as simple as that. But what problems will occur here in such simple methods? This resistance will change. If resistance changes, speed changes. This constant would be an issue. Right? This is for DC motor. Induction motor, it will be far more complicated. We have three currents, IA, IB, IC. We have three voltages, VA, VP, VC. Inverter output, current will be sinusoidal. That means current THD is less than 5% based on the PWM technique employed. However, the voltage THD is not less than 5%. Right? It is in the form of pulses. So because of that, because of this, many errors will come into system. Right? So you need to design. So they have designed something called observers, sliding mode observers and other observers. All these observers, right, they will have problem in terms of starting. At the starting time, the current is low, or you're running at low speeds, they will have problem. Right? So rather than that, you'll use AI. So what AI will do, whenever you find this speed sensor is not working, let's say this is your AI is a mathematical block, some set of mathematical equation, it will have two inputs. It will have IA, IB, and IC, the stator currents, right? And voltages, VA, VB, VC. So we have 1, 2, 3, 4, 5, 6. Based on this 6 outputs, it will give me speed. Right? So how this magic occurred, that suddenly from currents and voltages I got speed, right? So that is what I have to do. I have to make a data set for IA, IB, IC. Let's say IA, IB, IC. Similarly, VA, VB, VC, and then speed. So this is my output omega R. So I have to run my motor at different speeds for different loads. That means I have to run my vehicle at different speeds and different types of roads. Number of people sitting will change. Either it will be one person sitting who is very thin, one person who is little bit more weight, two people are sitting, because the weight of the vehicle, the mass of the vehicle determines the load torque. Right? The velocity determines the load torque. So I will test the vehicle for different conditions. Based on that, I will get a data set, and then I will do a black box modeling. That means for this input, what should be the output? Okay. But the beauty of AI is, see, we can make this in an Excel sheet and say, okay, now this is the current, this should be the speed. Okay. But where the different AI comes into picture is that even if the same values are not there, AI is able to predict if in between values are there. That is the beauty of AI. Suppose you run at 10 ampere and you run at 9 ampere, but what will happen if the current is 9.5 ampere? AI can manage that, right? Precisely. So one AI's effect comes to picture is for speed estimation. AI can play a role in speed estimation. Second, this, as I had said, this rotor time constant. The rotor time constant is based on the datasheet parameters or based on the tests on the motor. These values keep on changing with heat, with time, with aging, right? So what we can do, the AI can find out the precise value of rotor resistance. Rotor inductance does not change, but rotor resistance changes a lot. So it can precisely find out the value of this rotor resistance. Based on that, I can have accurate rotor time constant. Right? One more thing is PWM. Even this PWM can be shifted to AI. So AI will get these three as outputs: 1, 2, 3. The reference voltages. So AI will take those reference voltages and decide which switch should be on and which switch should be off. But we will say, okay, 3 comparators and 1 carrier was enough to that. What advantage AI has? AI can add optimal switching. By optimal switching, I mean AI will try to reduce the switching losses occurring. How the switching pattern should change so that the switching loss is minimum. Right? So this is a minimization problem. I have to minimize the switching losses. What are the constraints? The constraint is that the THD of the current should not be greater than 5%. It should be less than 5% at all times. This is the constraint. The current should not exceed the rated value. This is another constraint. So it becomes an optimization problem. Either you can use artificial neural networks or your support vector regression, right, a part of ML, or you can use meta-heuristic techniques. Right? These three can go into this. Again, I'm repeating, anytime you feel I've gone fast or I'm not, something I've said is not clear, please feel free to interrupt me. Right? Even if your suggestion, okay, can it happen like this, then also I'm fine with that. We can discuss that as well. Okay, one of my student is working on a different, one of my PhD student is working on a new thing we are trying to do here. What we are trying to do here. So this is a huge system. See, you are going to implement a control system on a DSP, and one of the problem in the DSP will be this theta. Whenever you do ABC to DQ, whenever you do ABC to DQ, or you do DQ to ABC, it involves trigonometric functions. Right? Our DSPs are not designed for that. They have to go to lookup table and then fetch and do. It adds to the complexity. Then PI is another problem. The tuning of PI. See, tuning of PI for a road condition electric vehicle is challenging because PI has to run at different, you don't know, different types of terrains are there, different weights are there, different speeds are there, different accelerations are there. The gradient, road might be flat, road he has to climb, he has to come down. So tuning of PI is a challenge, right? Then this is a challenge, right? Rotors, the resistance of the rotor, right? So what he is trying to do, he is trying to replace this entire system with one box, with one AI box, right? It is some mathematical equation. What are the input? Inputs are the stator current, IS, ABC, the three-phase currents, and input is speed, reference speed, right? This is a constant value, and actual speed, omega, right? Output will be gate pulses. Right? Then one student argued with him that if speed is the input, that means I need a sensor. If sensor fails, this system fails. So he did one more thing. He made two outputs. One is omega. Right? And the same output he took as an input, a delayed function. Undoubtedly, this system is not working great till now. It is having still many errors, and the root of mean of square of error, which is used to test this AI, is not as per our choice or as per our desired value. But we are trying to reduce this value so that the proper AI model can be built. We have those who are working in power quality. There is something called dynamic voltage restorer, which mitigates your sag and swell in voltage. So we have been able to employ that for that DVR, but we are not being able to still develop with the error as good as we want. So we are still working on this. Okay, coming to next point is direct torque control. This is how the direct torque control looks, right? It is different as compared to your earlier. It can be used for AC motors. It can be even used for PMBL-DC motor. Just to clarify, PMBL-DC motor is an AC motor, but it has a trapezoidal back EMF. So here you will sense current and voltage of the motor feed it to a torque and flux observer. Okay, these will generate the value of motor torque and stator flux, and they will be compared with the reference values. Okay, for induction motor, the reference value of the flux will be same as the rated flux, right? The reference value of the torque will depend on speed. Okay, and then your switching table. What does switching table do? It will say, okay, error of flux and we have error of torque. If it crosses some band that we have set, the limit that we have set, then you will get 1 or 0 or 1 and 0 and -1. Based on this, the switching table will decide which switch has to be on and which switch has to be off. When this operation, which switch is on and which switch is off, is happening, right, we are facing some challenges here. One of the challenges is how will you get flux? Let's say the flux for is obtained like this. Flux is equal to VSA minus ISA RA dt. One thing is there, VSA, the voltage here is in the form of pulses, right? So this will have high number of harmonics. This resistance may change, and the biggest culprit is inductance. Integrator. Integrator, if there is a small bias, right, this output will go wrong. This output value will go wrong, right? So can we have ANN based observer or support vector regression, that is ML technique, or many techniques are there, right? Based observer. That means it will take these as, this will act as a black box. It will take these two as input and give me torque and flux as the output. That can be one of the things. Can I optimize my switching table? That can be other scenario where my switching table, whatever the, which switch should be on, which switch should be off. Can I optimize that value? One of the biggest problems of DTC is, this hysteresis. This is a hysteresis controller. These two are. Okay. Hysteresis controller, if yes or no. If error is higher than this, switch on. If error is lower than this, switch off or go to -1. So these problems are there. So what do? They introduce torque ripples. That means torque is not constant, but it is like a chattering, So can we use ANN to reduce the torque ripple? Of course, ANN can be used to reduce the torque ripple. Right? This can be one more feature we can add. So these are the different, regression models we can implement. One more thing is there, switching table. So our next plan is this. We are going to build this for a EV. We will take current and voltage as input, and we'll have speed as input, and based on that we'll have classification problem. Classification means I've divided into classes. See how many switching conditions are there. There are 6 switching conditions currently. Right? 6 active switching conditions. Right? That means upper switch of A phase on, lower switch of B phase on, lower switch of C phase on. That is one switching condition. Similarly, there are 6 conditions are there. So we call that as state, right? So it can generate based on those 3 inputs. It will directly implement direct torque control and find out what is the value of S. S is the switching state. So how we will do it? First, we'll run the motor in direct torque control many times for different load scenarios. We'll make an Excel sheet or a data set in which the inputs are currents, IA, IB, IC, voltages VA, VB, VC, and speed omega. Based on that is a classification problem. My outputs will not be in a decimal. I will say it belongs to class 1, class 2, class 3, class 4, class 5, class 6. Right? That's S. This can be 1 to 6. So what does class mean? 1 means A phase, 3 legs are there. Upper switch of A leg on, lower switch of A leg off. Lower switch of B and C leg on, upper switch of B and C leg off. So this is one state. So next can be A upper on, B upper on, C lower on. Right? A upper on, C lower, C upper on, B lower on. So it can have different switching states. So different switching states can be employed with this AI based method. This is what we are going to target next. Right? So we have discussed about the propulsion system, which is mainly employed to take the power from battery, feed it to the motor so that we can control the speed of the motor. And by controlling the speed of the motor, we can control the motion of the motor. Whenever the vehicle moves, the motor is moving the vehicle and the motor is consuming some energy. So that energy is supplied by the battery. So as the vehicle moves, the battery discharges. And as the battery discharges, it also requires frequent charge. So the charging takes place at charging with the help of a charger. So let's have a look at how the charging system is, or how a battery charges. So this is a battery charging system. Here inside the box is a battery charger, your AC grid, right, which is supplying, and battery which is acting as a load. So as the name suggests, this is AC and our battery here requires DC supply. So what we'll do, we'll conform AC to DC conversion. So I'll get a DC here. Like I took the example of a diode rectifier. So what I'll do, I'll convert my single phase AC to DC. So I will get some DC output like this, the output of diode rectifier. Then I'll connect a filter capacitor so that I can get a straight ripple free DC, right? So this DC value will correspond to the peak value. For single phase, the peak value is around 325 volt DC, right? For this, so this will be 325 volt DC. But my battery requires 52 volt or 42, 48 volt. I do not need this high voltage. If I apply this high voltage, my battery will be damaged, and the battery damage can lead to accidental fire. Right? So we are employing a DC-DC converter. So input is DC, output is DC. We are going to control the voltage and current at the output. Okay? So this is a DC-DC converter. So AC to DC converter converts AC power from grid into DC. DC-DC converter converts, again, changes the voltage and current at the output, and these voltage and current at the output of the DC-DC converter are nothing but battery voltage and current. So it is going to control the charging of the battery. Either it can make current constant at the output, current remains same, that is constant current charging, or it can keep voltage, so we'll have constant voltage charging, or it can implement both. In actual practice, the DC-DC converter should implement both. One more thing is there, we need to connect filters here. Right? This will prevent the propagation of either switching harmonics into the grid, or somehow it will attenuate some harmonics. So this is general structure of EV battery charger. So you have AC grid and you need an isolation, so you'll have a transformer. So this transformer will reduce, let's say 230 volt to, let's say something like 35 volt or something, right? These filters are there. Then AC to DC converter, I will get here 35 into root 2 maybe, and then again DC to DC converter is there, and I can control the charging of my battery. So transformer here, what will be the problem with the transformer? This transformer operates at 50 hertz frequency. Because the transformer operates at 50 hertz frequency, it's pretty bulky. It is having high weight, it consumes more space. Because of the high weight and space, right? More materials are there, so material cost is increased, transportation cost is increased, manufacturing cost is increased, installation cost is increased. And we want our charger to be really bulky, right? Really compact, not bulky. We should not have an electric car and one more trailer is there, or one more car drives behind us which carries our charger. We do not want that. So what we will have, we want to eliminate this transformer. Right? How can we eliminate this transformer? That we'll try to see. So see here, AC grid and input filter. Transformer is not there. Then AC to DC converter. So here you will get, let's say, 325 volt DC. Then that DC, this is your inverter. So this is AC to DC. Then again you are doing DC to AC. Why we are doing DC to AC? Because here at the output, the AC will have 50 kilohertz or it will have 10 kilohertz, something like that. Very high frequency. Higher the frequency, lower the size of the transformer. So transformer will be really small. So we'll be using high frequency ferrite core transformer. So this transformer is really small. So at the secondary side also I'll get a 50 kilohertz signal, which will be converted to DC. So this is AC to DC converter, and I'll get a controlled DC here, which will be used to charge the battery pack. So what we did, we removed the transformer, which is operating at power frequency of 50 hertz. We replace it with the high frequency transformer. High frequency transformer requires high frequency AC supply. So for that, I implemented 50 kilohertz or 10 kilohertz. So first AC to DC, then DC to AC. This AC has 50 kilohertz. It works at very high frequency. Then this AC here will be induced here. Again 50 kilohertz to DC supply here. Then I will charge the battery. So different types of charging are there. AC chargers we have at level 1, level 2 charging. We have got DC fast chargers. We have got wireless charger. That means your car, in this again we have got static and dynamic. That means if your vehicle is, let's say you go to a mall and just park the vehicle on the charger below the ground, it will be there, it will charge the vehicle. Or else There'll be wireless charging is like you are going on a highway and you find that your battery is low. You go on a service road. Whenever you enter the service road, there will be some mechanism that will detect, okay, this vehicle number has entered. This was the state of charge, or this was the percentage charge of the battery. You drive slowly on the service road. There is a coil inside your vehicle at the bottom. There is a coil in the road. So one coil in the road will act as a primary. The coil in your vehicle will act as a secondary. EMF will be induced and battery will be charged. And that will be wireless charging. The only problem that we face is that the distance between the two coils, one in the vehicle and on the road, that is a big problem. Right? There is air which offers high reluctance. Moreover, are you properly positioning your vehicle on the coil embedded in the road? If that is not proper, then also the charging will suffer. So all these new parameters are there. And of course, we have got battery swapping technique where you simply go there and change the battery. Again, the chargers are classified as on-board charger and off-board charger. On-board charger means the charger is located inside your vehicle. Off-board means separate charger is there. So these are the different charging techniques that we have. Just to summarize this is the first charging technique where you have got it like this. Will start from here. Here you have transformer, right? Then AC to DC. Then you have got DC to DC, and you charge the battery. This transformer is working at 50 hertz. Right? I don't want this transformer, so I went to this. First, I went AC to DC, then DC to DC, and I'm trying to charge the battery. But this may not, work if the two voltages are not matching, right? So DC has to step down from a very high to very low value, which may not be very good for us. Then we are again going here. So this dotted line says that these components are inside the vehicle. Below the dotted line here, all the components outside. So here everything is inside the, this battery is inside the vehicle, right? So now, here if we check, see, below the dotted line inside the vehicle, battery, DC-DC converter, rectifier inside the vehicle. Here, everything is inside the vehicle except the transformer. Here, if you come, you have got AC to DC outside. AC to DC is outside. Then DC to high frequency AC is outside. This is your primary coil. Secondary coil is inside the vehicle. Again, you will convert AC to DC and charge the battery. Right? So these are the different types of chargers. We have onboard chargers, wireless chargers, off-board chargers, battery swapping. All these methods are there. Right? So commonly used battery charging techniques, we have two: constant current, that is CC charging, and CV charging. Right? CC charging is used to charge fast. Right, from 0% charge to 80%, we go for CC mode, and then we shift to CV mode. Right. So usually there is another term, state of charge, abbreviated as SOC. So whenever battery is in CC mode, that is constant current charging mode, when the SOC is less than 80%, we'll go for this mode. A constant current will flow into the battery and will try to charge the battery. But it may also cause heating of the battery. And if gaseous emissions are there, the battery will be permanently damaged. So we need to control that as well. So other alternatives, constant voltage charging, usually slow charging. Whenever SOC, state of charge, is greater than 80%, that time SOC is required. Right? So constant voltage will be maintained. So in order to do this charging, we need SOC. Right? So most common method is Coulomb counting method for SOC. For SOC estimation. This method requires simple data. It just requires your battery current, and you will integrate it and try to find out what is the charge. Right? So it will assume that initial charge is something you know. That means if battery was 20% charge and then you have started to charge again, that means initial information 20% charge was there, that it must be known to you. That is where the problem starts. We often do not know the initial charge. Some people said open circuit voltage of the battery. Based on the open circuit voltage of battery, we can find out what is the charge of the battery. That is absolutely correct. We can do this. But when to measure open circuit voltage, that is another problem. If you use the battery, then the battery to come to the relaxed mode, it may take 1 hour or 2 hours. That means after 1 hour or 2 hours, the open circuit voltage will tell you what is the charge in the battery. But before that time, it will not be able to tell you properly what is the charge in the battery. So this is where the first problem starts. So I would just like to add that AI techniques are not to be used when we can do something in a very simple fashion. Whenever some problem is there which is really challenging and normal methods cannot solve it, that time we should go with AI. So cool to find out SOC, these problems are there. Moreover, whenever we do integration, right, some other issues also creep in, right? If some noise signal is there, the integration will take that into account as well, right? So all these problems, if some bias is there in one of the sensors, then even that will be affecting your measurement. So for all these problems, we can go with AI-based SOC estimation. Right? I have a PhD student from a computer science background. She is working on this only, SOC estimation with different AI and ML techniques. So we'll have a look at that work as well. So this is the power circuit of a battery charger. So this part is your AC to DC converter. We have employed PWM rectifier. PWM rectifier means it performs AC to DC conversion, but at the same time, it ensures that these currents, input currents, are sinusoidal and in phase with the grid voltage. So you'll have unity power factor. Then you have this full bridge DC-DC converter. This part does DC to AC, but this AC is of high frequency, right? High frequency, and then again we have a rectifier which will convert to DC, and then we'll charge the battery. This is how this is going to work, right? So what are the problems in this? The problem is that whenever you go with switches, you need to have gate drivers, you need to have gate pulses, and it may add to the cost of the system. Right? So often diode rectifier may also be used. Right? So in this system, where our AI can come into picture in this type of system. See, this system to work properly, it has to control this voltage, VDC, first of all. Right? So AI can be used for VDC controller, as a VDC controller. So it can replace the PI controller. Also, if you want these currents to be sinusoidal and having power factor as 1, you need the information regarding the omega t, phase angle of the voltage. So this can be known by your AI. AI can be used to find out omega t or omega frequency. Then coming here, again we have to control. We have to find out what is the value of SOC. Based on SOC, you'll go for constant current charging or constant voltage charging. Plus, they are current and voltage controllers. CC controller and controller deployed for constant voltage charging, CV controller. All these can be employed with the help of AI. All these can be employed with the help of AI. That is the second thing. So I would just like to ask, you have a charging station. There are 4 charging terminals and 4 vehicles are getting charged. But what will your charging station do when only 2 vehicles are there instead of 4? What will your charging station do if there are only 2 vehicles available? There are not 4 vehicles. What will the charging station do? Any guesses? What will the charging station do if there are only one or 2 charger vehicles available to charge? The charging stations are waste, right? They are not going to do any work. They'll be simply lying there, right? They'll not be doing any work. They are simply idle. And because they're idle, you're losing your money. So can we think of multifunctional control? Can our charger do more than charging a battery? So whenever you want to do more than the battery, that time the multifunctional control comes into picture. Here, V2G stands for vehicle to grid. Okay, that means active power will flow from vehicle battery to the grid. That means you're supplying to the grid. Right? Similarly, grid to vehicle we have. That means power will flow from grid to vehicle. That means this is charging of the battery and this is discharging of the battery. So your V2G station will have different electric EV chargers installed, and they can do 2 things. One, they can take power from the grid and charge the battery, or they can take the power from the battery and charge the grid, or send it power back to the grid if the grid needs it, or you are getting better tariff. So you need to have an AI system. So how this AI system will work? Let's say you are coming every day to your college in the morning, going back to their home at the evening. So your home is, let's say, some distance away and you need at least 30% charge to go home. But your batteries, when you reach your college, you have used some 20% charge that day, morning traffic was less. So you come, you plug your vehicle into the charger and leave it there. Okay. So this, there will be a code for your vehicle, which the controller will know, the control system will know, okay, this is this vehicle, its SOC is this, the battery is fully charged. To go back, the data is stored on the cloud. This person uses this much charge is at least required to go back. That's a 30%. So it will, if more power is there, send it to the grid and keep 10% more, right? Just for some critical case. But if I send my power back to the grid, that means power is coming out of the battery and being sent to the grid. But battery is undergoing discharge cycles then. So battery has limited number of charge and discharge cycles. Right? So whatever power I'm getting in the battery, that time there are going to be some losses in my converter. So let's say 90% system is there. So I'm paying for 10% losses. But when I send my power back to the grid, again 10% loss was there. That is also borne by me. So if I do vehicle to grid in normal scenario, I am paying losses plus my battery life is reducing. It is not viable for me. But when will I do my V2G? I will do when I have got variable tariff. Right. That means I will charge my battery at, let's say, 5 rupees per unit. And when there is 8 rupees per unit, my battery will start supplying to the grid. So this is an entire system that has to be there. Right? AI-based system will detect which vehicle it is. What is the battery charge now? How much charge is required to go back? Right? What is the tariff? Should I send back to the grid and the vehicle will earn more, or no? The tariff is not very high to earn. Right? So this entire complex problem can be designed into an AI problem. Okay, when we are doing this, let's come back to the multifunctional part. What does multifunctional mean? Let's try to see that. So this is how the system is, right? I have my vehicle which has a battery installed. That battery is connected to, yes, I forgot to add this. For V2G, you require bidirectional DC-DC converter. You require bidirectional DC-DC converter. That means power can flow like this from battery to the grid during V2G and from G to V, charging the battery from grid to the battery. Okay. So when this battery was there, I am happy that it is getting charged or it is supplying to the grid, something is happening. But if battery is not there, absent, what this entire structure will do? This entire structure is waste. Right? So what I can do, at a battery charging station, there will be lights, LED lights will be there. There will be air conditioning system. There might be refrigerators, right? There might be pumps to fill the air in your tires. There might be some other loads. All these loads are non-linear loads. Most of these loads are non-linear in nature. Right? That means the non-sinusoidal current is drawn by them. So if your non-sinusoidal current drawn by these non-linear loads, then let's say current here is not sinusoidal, something like this. So you're polluting the grid. You're polluting the grid, right? So that is not something good. The grid pollution can cause problem to the others. For example, my cousin has an industry, and once we went to his industry, we tried to check how the current waveform was there, and the current waveform was something like this. And then pulses, all pulses square wave, and then again. Right? Some load he was having which was causing this during the negative half cycle. We tried to convince him that you install some mechanism for that load so that the harmonics are not coming into the system. He did not agree. Right? 2-3 months later, his servo stabilizer got permanently burned because of the harmonics. So this is a critical issue that we are facing. See, we want our grid to be more and more sustainable, more and more efficient. So that means because we want the grid to be more efficient, we want loads to be more efficient, we are going for energy efficient devices. Like here, energy efficient AC involves your permanent magnet motors, your inverters. Whenever inverter is involved, it requires DC supply. DC supply means your rectifier. So that rectifier again introduces harmonics. Right? I believe all of you had a long day and many of you must be tired, but it's really great that you are trying to attend the sessions and trying to, explore the chances for collaboration and new avenues to work on. So just to lighten the mood, I will just, match this with one movie story. In one movie, I have seen that there is a comedian who is not doing any work and everyone is screaming and shouting at him. 1970s movie, so less vehicles were there. So he decides that I will do some job. So what job he does? He opens a puncture repair shop. But he finds that puncture repair shop, if he opens inside the village, many people will come to him to repair. So he does not want to do that. So he opens the puncture shop outside the village, little bit away from the village, near the highway. No one comes to him. Still people say that you are useless. You are not doing anything. So what it does, every month he'll go 1 kilometer this side from his shop, 1 kilometer right, 1 kilometer left, throw the nails. Because he throws the nails, the tires will get burst and cars will come to him to get repaired and he'll get punctured. After that, he'll close the shop after that week, collect the nails and close the shop. Right? Power electronics is somehow something like that. We first try to find a problem, then we give a solution, then we again find a problem. Right? First we had battery charging. We said we'll charge the battery. For that, power electronics was needed. Then we said we want to shift the power back to the grid as well. So we built V2G. We bought in bidirectional DC-DC converter. Right? And now we are saying all these power electronics energy efficient devices are causing current harmonics into the grid. They are drawing non-sinusoidal current. So that is, so you have one power quality device. So power quality device is again a power electronics based device. So we want this current to go out of the picture. This current to be sinusoidal. Not only sinusoidal, but power factor should be unity. So we'll go for multifunctional control. What does multifunctional control say? Multifunctional means it does two functions. One, it sends the power to the battery. One, power from battery to grid, or power from grid to battery. So either it will charge the battery or it will perform V2G. So this is V2G and this is charging. Second, it does harmonic current mitigation. Some messages there. So it does harmonic current mitigation. What does harmonic current mitigation mean? Your non-sinusoidal current, let's say this is the current, is divided into two parts. One is sine wave and other part. Sine wave plus other part. Right? So what we will do, so what we will try to do in this, we will try to select the sinusoidal part. Just 1 minute. So what I will try to do, my current has two parts. Okay, my current has two parts. This is the non-sinusoidal current. Where the non-sinusoidal is coming, current is coming from, it is here for the load. This load is drawing non-sinusoidal current. I cannot change my load. So what I will do, I will decompose this into two parts. One is sine wave. That is what Fourier series says. Any periodic waveform can be decomposed into sine wave, having multiple fundamental frequency and integral multiples of fundamental frequency. So that integral multiples of fundamental frequency are harmonics. The others are here harmonics. And reactive component. Right? So harmonic power is very small. Harmonic power is very small. So what we'll try to do, we will ensure that the current flowing into the grid, let's say for V2G, we are performing V2G. So current flowing into the grid is the current supplied by the battery, which is, this is your VSI, voltage source inverter. So current will be AC current. And this current is sine wave, right? This sine wave, we are doing grid synchronization. That means the current frequency and phase matches with the voltage. So for A phase, the phase angle and the frequency are same as the voltage VSA. Plus the harmonic currents will be there. So what will be the impact? Now the harmonic current is coming from this battery to the load. So load needs harmonic current. It does not matter, it takes from the battery or grid. So load will say, okay, I have got harmonic current from the battery, I don't need from the grid. So grid current will be purely sine wave. That is the multifunctional control. So we are doing two things. We are improving the power quality and we are performing V2G or G2V. Right. So this is the power circuit of the EV charge, and this is the control system I'm trying to explain. So we will have the voltages, grid voltages, VA, VB, VC. It will be fed to the PLL. What does PLL do? It will find out the theta, the phase angle, but phase angle of positive, fundamental positive sequence component. The phase angle of fundamental positive sequence component will be found out. Right. So that is what we have achieved. We have done that. Right. So this can be replaced by AI. Okay. It can be ANN. It can be better than ANN. You can explore this. ADLINE. ADLINE. It stands for adaptive linear neuron. It is a type of neural network. It is very much suited for this PLL. Then we'll have UVT generator, unit voltage generator. That means we'll have sine theta minus 120, sine theta minus 240, sine theta minus 120, things like that. Right. Then we'll do fundamental active current extraction. That means we'll find out the part, these are the load currents. Check, these are the load currents. So from load current, I said is two parts. One is sine wave with 50 Hertz frequency, and there are other components. So I'll find out the sine wave. What is the magnitude of peak magnitude of this sine wave? This represents the peak magnitude. Right? So this peak magnitude will be multiplied by sine wave, means this much current ILFAC into sine theta. If I draw from A phase, then the harmonic will be taken care. Okay. So all of us have heard about FFT, right, or DTFT or Fourier transform, right? FFT is used to find out the harmonics. What are harmonics are there, and based on that we can control. Okay. But what is the problem with FFT? FFT requires one entire cycle. It requires one entire cycle. So one cycle of 50 Hertz is 20 milliseconds. So I will take my corrective action after 20 milliseconds, which is very bad. Right? That for 20 millisecond corrective action is very bad. So what we try to do, we try to use other methods. So standard methods are synchronous reference, SRF, synchronous reference frame theory method. This is a standard method, but this method is again very slow. It is a problem. So we can shift to AI based systems. So we have tried to explore different AI algorithms. Recently also, with the help of some students, we are writing a paper on, we have used the data and try to find out based on that, what is the sinusoidal component? What is the peak magnitude of the sinusoidal component? So I'll show you those results. And we found out that deep learning gives me the best results for the given condition. So coming to that, this is what I'm trying to show. This is the peak magnitude of fundamental active component of load current, FAC. Right? For different algorithms, 1, 2, 3, 4 methods are there. Right? At this point, I have changed my load. So current changes. See, the current immediately comes. In 10 milliseconds, it reaches the new value. Here, 10 millisecond, method 2. SRF, the standard, it takes 13 milliseconds. But if you go for 13 milliseconds, check here. There are ripples. It is not constant. Right? There are some ripples. This will have detrimental effect on your control. Right? If you go with 10 Hertz, it gives very smooth waveform, but see the response time, 60 milliseconds, very high. Right? So this is not something we want. So here you can use AI. You can use particularly ANN can be used. You can use support vector regressions. You can use deep learning. You can use. Right? The different methods are there. Right? So you can just go to MATLAB. MATLAB has got a regressor app, support vector regression app. You can just feed the input data, output data, give it to the regressor app, and the support vector regressor app will run for all algorithms possible and tell you which algorithm is the best suited. Okay, but only, at least I don't know, I might be wrong, but till now for my problem I have not been able to solve is that this regressor app can have only one output at a time. So if you are going for 3-phase system and you want 3 separate values of IFAC for each phase, then you have to run it for 3 times. That's the only trouble. So these are the waveforms that we got to simulation. I have hardware waveforms as well. So this is my voltage. Voltage is sinusoidal. These are load currents. You can see load currents are non-sinusoidal. And these are the injected currents. That is means I am doing active power injection. That means I am sending power to the grid. Power to the grid is sent from the battery. So this is V2G. And I am doing shunt compensation. That means I am mitigating the harmonics. See, the current being sent from my inverter is non-sinusoidal. Why? it is non-sinusoidal because the harmonics needed here by load current are supplied from here. So from here harmonics are going, right? And see, because of that, my source current is now current from the grid is purely sine wave. Current from the grid is purely sine wave. Right? What new thing other than this we have done? We have implemented partial compensation. What does this mean? See, your inverter has some current, maximum current rating. You cannot exceed that current rating. Okay. Now for shunt compensation, for shunt this harmonic current mitigation, let's say you're already supplying 10 ampere current is being supplied for V2G. And my maximum permissible current is 12. Only 12 ampere I can send. So I only space for 2 ampere capacity, hypothetically. So I can increase the current only by 2 amperes now, peak value of current only by 2 amperes. So what I will do, I will check if I go for fifth harmonic mitigation. Is it okay? Is it exceeding the 12 ampere limit? No. Go for seventh also. Is it exceeding? No. Go for seventh. Add 11th. Is it exceeding? Yes. Then stop. Only compensate for fifth and seventh. Don't go for 11th. Right? So that is why you will see these currents are non-sinusoidal. These currents are non-sinusoidal because it's sending fifth and seventh. But other harmonics are coming from the grid. So now grid also has harmonics. Why grid has harmonics? Because my system is not able to handle the harmonics. Right? My system is not able to handle the harmonics. But still I'm doing somewhat better than what the THD for this check, it is 16%. Right? The grid, it increased. So this is something the disadvantage we are having. Why this problem occurred? Because we did not reduce the harmonics from the grid. So grid is now supplying 11th, 13th, and so on. But the active power that was delivered by the grid, that is also reduced. That means now the fundamental current is coming from here. Let's say 60% of the fundamental is coming from the battery. 40% is coming from the grid. So what is THD? THD is sum of square of harmonic currents divided by the fundamental component. Fundamental is reduced. That is why harmonics has increased. Right? This is not degrading the system, but because your fundamental has reduced, that is why your harmonics have gone high. Any point of confusion here? Okay, then I'll go for the next part. Other area we can work on is something simpler like this. We have EV charging station. You have some load at EV charging. Lighting load is there, air conditioning is there, pumps are there, right? Water supply system is there, air pumps are there, right? Refrigeration unit might be there, because we are now planning that EV charging will take more time. It is not like you go there and immediately it charges. Right? EV charging will take some time. So people are thinking that we'll open a food outlet there, a shopping complex there. So you go there, do the shopping, eat food, come back, electric vehicle is charged. So all other loads that we are having are also non-linear. So here current will be this current coming from the grid here, right? And this is current, load current. This is load current. So these are non-sinusoidal. Okay, these currents are not sinusoidal. But if you have non-sinusoidal current, it will have a huge effect on the grid. One, power transfer capability of the grid will reduce. The overheating of the cables will be there. There will be malfunction of the protective equipments. Protective equipment will not be able to operate properly, right? The efficiency of the distribution network will reduce. Life of certain equipments will be compromised. Right? So all these problems will occur. So we want this current to be sinusoidal. So this is my charger. So what I will do, I will install shunt active power filter. What shunt active power filter does, it checks load current. Load current has two parts, sine plus harmonics. Separate them. Separate the two parts, right? Just 1 minute, it seems my PC is causing some issues. So we'll separate these two parts. Right? So the two parts will be separated. I'll separate out sine and fundamental component. We can do it here also. I have got sine component plus fundamental, plus harmonics. Where for this currents, right? I cannot stop harmonics, okay, because load is demanding. But what I will do is separate them. That means now I've got harmonics, I've got the sinusoidal part. This active filter is nothing but an inverter. Active filter is nothing but an inverter. I will control this inverter so that these currents are equal to harmonic currents. That means load is getting harmonic current from the active filter and this current is supplying only the sine wave. So I'm getting the power quality enhancement. Right? That is also possible. So for this, how to separate? That is the issue. So how to separate is the issue. For this, we can use ANL. We can use support vector regression, SVR. So you find out the different current waveforms. You feed those current waveforms to an FFT block in MATLAB or a PSCAD. You find out the fundamental part, right? So actual minus fundamental will give you harmonics. Now train your ANN or support vector regression for this. So what will happen if we install SAPF at the charging station? Before that, we'll check this. SAPF will does neutral current compensation if unbalance is there. See, this is another aspect. If your load is unbalanced and it is damaging the grid, we will do neutral current compensation. We can have harmonic current mitigation. That means harmonics will be provided by the active filter. Plus reactive power come. That means reactive power needed by the system will come from here. So here the power factor will be unity. Right? Power factor will be unity. That is another thing benefit we can have. Increase power transfer capability of the distribution network. So we don't want our EV battery chargers to play with the power quality of the grid and spoil the power quality there. Right? So these are the advantages we can have. Right? So 5% THD will be below 5%. This is the limits we have. Unity power factor at supply end. Current drawn by the charger from this here, from the grid, will be sinusoidal and in phase with the voltage, plus it will be balanced. So this prevents grid pollution, this prevents unbalance of the grid. Right? That is the benefit that we have. So for control of SAPF, I will just summarize here. So our phase lock loop, this can be replaced by ADLINE, adaptive linear neuron. That is the short form is ADLINE. Right? This fundamental active current generation can be artificial neural networks, or it can be support vector regression. Right? This hysteresis current controller, this can be go for SVM, support vector machine. It will classify. This entire thing can be a classifier. Classifier means it will have 6 states, 1 to 6. Each state means what should be the switching sequence. The state means switching sequence. Which switch should be on and which switch should be off. So switching sequence will be generated here. Right? So this can be a classifier. Yeah, just because of we have less time, I'll just show you the results somehow. So this is the algorithm we had developed. Right? So this huge algorithm we had, and we faced some issues, mainly when the unbalance was there with this algorithm. So we had to come up with this formula for unbalance, and this is for balanced. And this is for unbalanced. Okay. But how to know what is balanced, what is unbalanced? We can add the 3 currents and find out how much unbalance is there. And if the unbalance, so one is unbalance is there or not there. Other thing is what is the degree of unbalance? How much unbalance is there? How much percentage unbalance? Based on that, your algorithm changes. So this adds to the complexity. Can we replace this with a smart AI base? By smart, I mean it will find out what is the percentage of unbalance, and accordingly it will modify these 2 equations. These 2 equations will be modified accordingly. Right? That is what we have aimed at. Yes, so I'll just quickly go to the different. Okay, so further AI applications we are trying. We already seen for this, right? I'll just show you this. So for sensorless speed estimation, means without having a speed sensor, we are trying to find out the speed. So different algorithms are there. So first I tried with sliding mode observer. See, this is the waveform it came. First my system was perfectly tuned, and then it was a PMSM motor. This is the waveform I got. See here, the problem is here. It is not proper. Here also overshoot is there. So I want my speed to increase from 0. 1500 is my reference speed. Go here and settle here, not go above this and slowly come down. Right? So this was caused because my PIs were properly tuned, but when I introduced sliding mode observer for sensorless speed control, this problem started. Similarly, I started with superposition theory based observer. See, again, this problem was there, and it slowly settled at a reference speed, but the response was better. When I went for high frequency signal injection technique for sensorless operation, the waveforms were still poorer, and I had more problems. See here, the speed is not proper. Here also speed is not proper. So I went with ANN based system. Just check the time, okay? It is settling, let's go to this. It is settling somewhere at 0.4. Right? It reaches the final speed at 0.4 millisecond. Sorry, 0.4 second. And what we did with ANN? This is, we developed a new controller, neural system structure based controller. Right? How it did? See the response. First it was settling here, 0.4 seconds, speed was reaching. Now speed reaches very fast, less than 0.1 second. And see, the actual speed, you cannot see the red and blue different because they're superimposed over each other. Right? Blue is the estimated speed. Little bit variation is there. You can see chattering, little bit of chattering. Other than that, that neural system structure-based system is working fine. It will estimate the speed and control the speed. Both it is doing. So ANN is able to, it is not exactly ANN. We have made some modifications to ANN and we called it a neural system structure-based control. See, ANN, what we have to do, we have to train the weights. So if I simply tell ANN is like this is a neuron, or I'll call it this is the activation function. This is an activation function. Right? So it has some mathematical function. Let's say f of x is equal to hyperbolic tangent of x. And it has an output y. Input might be multiple. Let's say x1 is the input and x2 is the input. And each input will have weight w2, w1. So y will be function of, let's say, z. And what is z here? Z is w1, sorry, tan h. So tan h is this. Z is w1 into x1 plus w2 into x2. So what will be y? Y will be tan h w1 x1 plus w2 x2. And this is simplest I have shown. There can be hundreds of neurons or tens or hundreds of neurons. Based on this computation will keep on increasing. Right? Let's have an application. Let's see a neural network for, as I said, to separate out the harmonic components. So here output is u of, input is u of n and u of n minus 1. That means previous sample. And I have used non-linear autoregressive exogenous NARX feedback neural network algorithm. So input, I'm taking, what are the inputs? What does U stand for? U stands for ILX. X is for A, B, C. That means I will have A, B, C load currents. Then UVT, that means sin theta minus 120, sin theta minus 240, that are the inputs. And compensating current, that means current supplied by the active field, that can be taken. And this is one more. I have applied this current to a low pass filter and found out what is the value. So all these are the inputs to this, and this is the neural network block. So input will be given, scaling will be done, every variable will be bought between -1 and 1. Then weights will be multiplied. Here summation of weights will take place. I will add bias here. This B stands for bias, I'll add. Then I will send it to the activation function. This is my activation function, right? All inputs are multiplied by weights. They are added, bias is added. Then I'll get E of P. E of P is sent to a hyperbolic tangent function, and hyperbolic tangent function will try to find out a value. Again, I'll multiply that value by weight. If there are more hyperbolic tangent 10 functions, I'll get 10 outputs. 10 outputs multiplied by VQ. Then again I'll add bias. Again I'll, due to the linear activation function, and then I'll get the output. This is how it works. Right? I'll quickly show you the output and how it came. These are the details of the neurons. There were 20 inputs. One hidden layer was there. 10 neurons in hidden layer. Weight matrix was 20 cross 10. Activation function was tan h. Number of outputs were 4. Output neurons were 4. Size of weight matrix between hidden and output layer was 10 cross 4, and linear activation function was there. This was modeled in MATLAB and simulated. Right? I got the error of 9 micro. So see, this is the current, load current we have. Right? This is the supply voltage. It is distorted. My source current is sinusoidal. These are my harmonic currents, and this is my estimated current. Based ANN found this out. Right? This results in my source current PhD is, sorry, this is not 32%, not 3.2, is less than 5%. This is less than, that is what I needed, right? I'll just quickly go through certain slides, right? Application battery charging, this is what I was talking about, the data-driven method, where SOC estimation takes place. So we want to find out the SOC of the battery. So what we did, we bought different cells, organized the cells, and then collected the data. And based on the real-time data, we tried to implement ANN and try to find out. That was the first step. But what we found out, the battery characteristics is highly non-linear. So we employed SVM, right? Support. So we found out this is region 1. We made this region 2 and this region 3. Then we use support vector regression to find out the battery is operating in which region, 1, 2, or 3. And based on the 3 regions, we had separate neural networks for each. It gave us better results, right? So I believe I will stop here because the other session is going to start. So I'll just come to key takeaways. For EVs, EV AI can be employed for speed control. It can be applied for current control. It can be applied for sensorless speed estimation or current estimation. Sometimes the current sensor goes bad. It can be used for current and voltage control for battery charging. It can be used for SOC estimation and SOH estimation. As I said, for shunt active filtering, what we call it multifunctional control. For that, it can be used for FSCL extraction. That means what is the peak value of the sine wave component. There are different modes in V2G, right? We can be used for seamless transfer between the different modes. It can be used for frequency and phase estimation, that is PLL, and unmanned vehicles. Okay. Other thing, what I observed from my work, that ANN and fuzzy logic are more explored. ML is less explored in EVs, more focusing on simulation studies. We need to come up with the real-time application because it is very complex, right? Our DSP, can it handle that? Because our DSP will be running at sampling frequency of 10 kilohertz, that is 0.1 millisecond here. Can our algorithm for controlling a EV plus AI run within this time, or separate DSP is required? That is a question. Whenever we go for some optimization, AI-based optimization, that will be a critical challenge. Should we go put the data on cloud and go for online training, or we need to go for optimization, online optimization there? So these will be the challenges, right? So I have come to the end of my talk. I hope you found it useful, right? Feel free to write me, email me anytime if you would like to have further discussion on this, or you would like to collaborate, or you would like to use some of the facilities that we have. Thank you very much. I'm stopping my presentation. Over to you, sir.
Thank you, sir.
I hope I have adhered to my time limit. Over to you, sir.
Please, sir.
Anbu? Yes, sir.
Shall we conclude the session, sir?
Yes, sir. Yes, sir.
Any other points, if any other doubt, please let me know. I'll be happy to address them.
Participants, if you have any doubts, you may unmute your mic and you may raise your questions. Participants.
So I'll put down my email ID in the chat box in case if anyone like to have discussion at later point of time.
Good, sir.
Yes, sir.
Shall I conclude the session, sir?
No, yes, sir. Okay, sir.
So thank you, sir. So as we conclude this insightful session on role of AI ML algorithm in electric vehicles, I take this opportunity to express my heartfelt gratitude to our esteemed resource person, Dr. Amit P. Sant, Associate Professor and Pandit Deen Dayal in Energy University, Gujarat. Sir, your insightful and engaging session has greatly improved our understanding of how artificial intelligence and machine learning are shaping electrical vehicles. Your expertise on electric propulsion systems, speed control techniques, EV charging methods, V2G, multifunctional control, and AI applications enriched our understanding immensely. On behalf of SR Madurai College for Engineering Technology and the entire Atal FD organizing team, we sincerely appreciate the time and effort you dedicated to sharing your knowledge with us. Your valuable ideas will surely encourage more learning and research in this field. A big thank you to all the participants for your great involvement during the session. Your participation made this discussion more valuable and engaging. So once again, thank you, Amit sir, for your invaluable contribution, and thanks to everyone for being a part of this session. So we look forward to more valuable discussions in today's next session, starting at 7:35 p.m. Before we conclude, participants are kindly requested to fill out the feedback form from the link posted in the chat box. Thank you.
Amit sir,
Thank
thank
you.
you, sir. Thank you
Thank
very
you,
much,
sir.
sir.
Thank you very much. It was a
Very
great
nice presentation, and you are fully informative, and we learn a lot of things from you, especially for V2G and G2V. That's nice presentation, sir.
We have
We
made a
will-
hardware setup. Whenever you are coming to Ahmedabad, please give me an email. I will show you the setup. I'll run the hardware setup for you.
Thank you very much, sir, for
Thank
your
you, sir.
help. Thank you.